So in our last video, we just went through sine, cosine, and tangent and looked through the different characteristics of these functions by exploring the GeoGebra activity that I had put on iLearn, right? We're going to be looking at the quote-unquote inverse operations now, so that we can see if there are any relationships between its inverse, like such as is there a relationship between cosecant's characteristics and sine's characteristics. And then also generally, let's look at if we have any asymptotes, domain, range, period, if it's even or odd, using the test that we've been using over these past couple units. So let's look at this, right? If we have y equals cosecant of x, we want to think about what does it look like. So what I'm going to do is I'm at cosecant of x, and I'm going to unwrap the unit circle so that I can determine what the function actually looks like, right? So I'm going to unwrap the unit circle by moving my slider around, right? So here's what I'm noticing. I see that they kind of look like parabolas, like they look like U's, right? They're not really parabolas. But I notice that I do have some asymptotes, right? I have these boundary lines, and I notice that I only have the curve between these boundary lines. So let's look at where these boundary lines are. It seems like I have one at pi and I have one at 2 pi. So if I take the difference between them, it looks like my period is going to be pi, right? So I know that my period is going to be 1 pi. So I already got that down. Okay. If I'm describing how it looks like, right, we know that this is a periodic function, right? We see that we have one kind of u over there, we have another u over here. If I go down a little bit, right, we see that this pattern continues. I have this full graph of cosecant of x. So I know that this is also a periodic function, but it's not a sinusoid. And we see that we have some asymptotes, right? We just talked about those boundary lines at pi and 2 pi, right? So if I'm thinking about how can I generalize where my asymptotes are going to be, I'm just going to pick, let's say I'm going to pick 0, or actually no, let's just pick pi. And then we're going to multiply it by any value n. Okay, so that was kind of shaky. So let me just explain my thinking behind this. So I see my first boundary line actually, like, it's kind of hard to see, but it's actually at 0, right? And then I know that I can always recreate my boundary line by adding pi, or my period, times a constant, right? This is why I determine the period, because I'm seeing every time my curve reoccurs, right? So if I'm starting at 0, and then I'm adding pi times n, like any value of n, right? Obviously, I am just going to be left with pi times n, right? Because 0 plus anything is just going to be, whatever you have. So our asymptote would just be at x equals pi times n, right? So then as a result, our domain would be every time we have an x value that doesn't include those asymptotes, right? Because we see that we can keep going infinitely to the left and infinitely to the right and still have our curve. So if I'm describing my domain, that's going to be all real values except when x equals pi times n, right? And this pi times n is coming from the asymptote that I created, and the asymptote was created based on looking at the period. So let's talk about the range, right? Do I go on forever and ever and ever in both the positives and the negatives, right? And I kind of do, right? So like if I look down over here, I see that if I keep going down, I keep going down into negative infinity. If I keep going up, I keep going up to positive infinity, but there is this little gap over here. And let me just look at this graph over here so I can see it a little bit better. So I see that there's a gap between 1 when y equals 1 and when y equals negative 1. So we can say that it's all real values excluding those values between negative 1 and 1. So all real values except when we're between negative 1 and 1. And so let's kind of think about, like, where did we see, like, where does this exception in the range come from? And we can see that that actually corresponds with the range of sine of x, right? Sine of x's range is between negative 1 and 1, right? So it's kind of, if we took like a little curve, right, and we're able to draw all the curves between here, right, we would actually be able to draw sine of x. So that's something that's kind of cool. Okay. And then we have our test to see whether or not cosecant is going to be even or odd, right? So one thing that we can do, right? I'm going to zoom in so that my origin is at my center, right? And here's what I'm going to do. I'm going to create an inequality where I'm looking at all the values of x greater than 0 so that I can look at the right-hand side of the y-axis. So if I do that, okay, and I want to see, does the right-hand side look exactly like the left-hand side? No, it does not, right? I have this curve facing upward on the right-hand side above the x-axis, and I have this curve facing downward below the x-axis on the left-hand side, right? So I know that they're not symmetric, so I know that this is not going to be an even function. My hunch would be that this would be an odd function, right? Because this is the inverse function, quote unquote, inverse function of sine, right? And sine is an odd function. So let's use our test, right? If we put in this function where we negate the y, we negate the input, and we're rotating around the origin 180 degrees, right? Then we should end up just seeing the same curve on this graph, right? That would mean that you have an overlapping function. So let's try this out, right? So I have negative y equals cosecant of negative x. Okay, and I only see the one curve, right? And let me prove to you that I'm not lying, right? Let's say that I get rid of the negative sign with the input, right? I have a totally different curve, right? So in order to actually create this shift where we are rotating around the origin 180 degrees, we need to also negate the inputs. So passes our odd function test, so we can say that this is odd. And like we said before, it doesn't necessarily have to be even or odd, right? But there are a couple tests that we can do to determine if it is even or odd. Okay, let's look at secant of x. So here we have secant of x. Once again, I'm going to unwrap my unit circle to see what the graph of secant of x looks like, right? So, okay, it looks pretty similar to cosecant of x, right? And that's something that we would expect, right? Because secant of x is the inverse function of cosine of x, right? Cosine of x looks pretty similar to sine of x. There are a couple of key differences, right? And just like before, I noticed that there's a boundary line, right? I noticed that there's a boundary line at pi over 2. I noticed that there's one at 3 pi over 2. Right, so if I take the difference between these, I can determine that my period is 1 because 3 pi over 2 minus pi over 2 is 1 pi, right? So my period of secant of x is going to be 1 pi. There we go. Okay. And then let's just describe what it looks like, right? Like we said before, it looks pretty similar to cosecant of x, right? So we know it's a periodic function, and it's not a sinusoid. Okay. So let's try to determine what would our asymptote formula, like generalized, be. That was a bad sentence, but you know what I mean. Let's try to generalize the formula for finding the asymptotes of secant of x. So if I'm trying to establish a starting point, right, I might say I might actually just start at pi over 2, right? So I'm just going to start at pi over 2 because that's the first boundary line that I see. So x equals pi over 2. And then what I can do is I can just add my period to find my next asymptote, right? So times 1 pi. And then I think I could keep doing this, right? I could do plus 2 pi n plus 3 pi n, right? I can just multiply it by any constant, right? And then I will end up with my asymptote. So my domain would then be all real values except for when I have those asymptotes. And let me just confirm. So I'm going to look at the bottom graph. I'm just going to zoom out a little bit. And yeah, it goes on for all real values for my domain. So I'm just going to say it's going to be all real values except when x equals pi over 2 plus 1 pi times n, right? And let's try to just create some intuition between, like, you know, why are we starting our asymptote formula at pi over 2? And remember that secant of x is the inverse function of cosine of x. And so if we're thinking about, you know, when do we first have any kind of dip, okay, I'm just going to cut that out. Okay, so okay, so we just determined our domain, right, based on looking at the graph and then also kind of exempting the asymptotes that we created. Okay, So let's look at the range, right? So if I scroll down here, right, I notice that I can go down to negative infinity, I can go up to positive infinity, right? My function is this. It seems at all real values except there's a gap, just like how there was for cosecant of x, right? And I see the gap is actually pretty much the same, right? It's from 1 to -1. So I'm going to write my range just like how I did for my cosecant of x function. So I have all real values except between -1 and 1. Okay. And you know how I was saying before, like, oh, you can actually like kind of graph your, the inverse function of secant of x or the inverse function of cosecant of x between these curves, right? And you can. So if you show the cosine function, right, you see that it actually exists between these curves. Oops, did not mean to zoom in. Let's try it over here, right? Sine of x should exist between these curves. And that's because you're basically graphing everything except for where sine of x would occur, right? Great. Now let's move on to cotangent of x. And so once again, I'm going to unwrap this. Oh, actually, sorry, I did not determine whether or not this was even or odd. So based on secant of x being the inverse function of cosine of x, cosine of x is even, so I would expect secant of x to be even. So let me just move into this graph. Whoops. Let me move in. And so when I move in, here's what I'm going to do. I'm going to center my origin in the middle, right? I'm going to actually zoom out a little bit so I can see this a little bit clearer. Okay. That seems like the origin is pretty much in the middle. What I'm going to do is I'm going to draw a boundary line. So x is greater than 0, so I can see, what does it look like on the right-hand side? What does it look like on the left-hand side? My right-hand side, if this is even, should look exactly like my left-hand side, right? And it does, right? If you were to fold exactly at this boundary line, they would overlap each other perfectly. So we can determine that secant of x is an even function because of that. Now let's look at cotangent of x. So if I look at cotangent of x, right, it actually looks pretty similar to tan of x, except just like reverse, I guess. And so let's actually unwrap the unit circle to see what cotangent of x looks like, right? Okay, so we see those boundary lines once again, right? So we have those asymptotes, and I know there's one at pi, and I know there's another one at 2 pi. So same kind of thing. It's a periodic function, not a sinusoid. So if I take the difference between those two boundary lines, I can determine my period, and so that's going to be 1 pi, right? Because 2 pi minus 1 pi is 1 pi. Okay, and then I see that my boundary lines are actually, we've seen these boundary lines before, right? When we were working with cosecant of x, right? So it's just going to be the same general formula for our asymptotes, where it's going to be pi times n. I know this because my boundary line starts at 0, and then I add my period times a constant in order to determine my next interval, right? And I should be clarifying that this constant that I'm multiplying by, it has to be an integer, right? It can't just be like 0.5 because you're not going to get the boundary line, right? If you did pi times 0.5, at half pi, you don't have an asymptote, right? So that wouldn't exist. So your constant has to be an integer. Okay, so we can determine our domain, right? So it's going to be all real values except where we have those asymptotes, except x equals pi times n. Great. And then if I look, if I zoom out a little bit, right? So let me go to my graph. If I zoom out, seemingly exists like I exist all real values going to the negative, going to the positive. So I'm going to say all real values. Okay. We said that tangent previously was odd, right? And we did the odd test to kind of determine that. And because cotangent of x is the inverse function of tangent of x, I would expect this to also be an odd function. So let me just see. I'm going to do my odd test. So I'm going to negate my output. I'm going to negate my input. And then I should end up with a graph that is exactly like the one that I have right here. So I shouldn't see any other graphs. And yeah, looks like I do, right? Yeah, so because they overlap each other, right, we can determine that this is actually going to be an odd function. Right. So that is the entirety of your table filled out. If you have any questions, just reach out, and yeah, good luck.